We're going to finish up Chapter 8 with Section 3, looking for the confidence interval when sigma is not known. This is a more normal situation. This is a situation you're going to run into when you're working on your final project. So in order to do this, again, our objective is obviously find the confidence interval for one population mean when sigma is not known. We're going to get a new distribution. So we've looked at the binomial distribution. We've looked at the normal distribution. Now we're going to learn one called the t-distribution that's going to help us with this problem here. So what we've been doing to find these confidence intervals, we've been using the standard normal distribution table. So we've been finding the standardized version of X bar, which basically we're finding the z-score. So we're taking X bar minus mu divided by sigma over the square root of n. Because this sigma over the square root of n is going to be the standard deviation for our set of sample means. So when we don't know sigma, we're going to estimate it with our sample, which is, again, the whole idea behind the inferential statistics. So we're going to use S as the sample, or the standard deviation we get from our sample. And so when we change this from sigma to S, we're going to change this to a T instead of a Z. And this is called the studentized version of X bar. Now, we've been doing all of this. We can assume normal, we can assume normal, we can assume normal. We can't assume normal for this. This is not a normal distribution. So we're going to get a new distribution, and this is the t-distribution. So with the normal distribution, we can say, give me the mean, the standard deviation. I can define the normal distribution. The t-distribution is defined only by one number, and that's we call the degrees of freedom. And the degrees of freedom is based on the sample size. We take the sample size minus 1, that's the degrees of freedom. And that's all we need to know to find the t-distribution we need to work with. Now, again, this is a free distribution, so we look at a density curve. The total area under the t-curve is 1. This is important to be a density curve, so we can get our probabilities off of this. As a curve extends indefinitely in both directions, it never touches horizontal axis. It gets closer and closer to it. Again, it's a density curve, but it is symmetric about 0. So with the standard normal curve is symmetric around 0. Any other normal curves are symmetric around their mean. The t-curves are all symmetric around 0, so we don't need that bit of information. It's a t-curve is a t-curve is a t-curve. It's symmetric about 1. It's only changed by the degrees of freedom. So as we start with 1 degree of freedom, you notice the green one is your normal curve. The blue is your t-curve with 1 degree of freedom. And if you notice, it doesn't hit the 3 standard deviation rule. You look at the majority of the data, a lot of the data is within 3 standard deviations. But if you're looking there, it's getting quite a bit. There's still quite a lot that's going to be under that curve after 3 standard deviations. But as we even go up to 5 degrees of freedom, you notice that red curve is getting pretty close to the green curve. It's still, if you look at 3 standard deviations, there's still quite a bit more. It's not like the green one, which is practically at the x-axis by the time you get to 3 standard deviations. But again, the more degrees of freedom you have, the closer this is looking like a normal curve, which kind of fits with our idea we talked about before, that the larger your sample size is, the more we can say, even though this isn't normal, we can assume it's normal. We're seeing this even with the t-curve. So when we look at the table, again, we don't have this standardized version that we can use one table for everything, because that degrees of freedom makes a difference. But where we're using the t distribution is mostly for this idea of confidence intervals. So we don't really need the whole table. We just need, the values you use the most. Again, you can use technology to get any value you want. But for our purposes, we're going to be using this table here. And it's table 4 in your book. If you go to the back page, the back inside cover has your normal table. If you flip over one page, you get this table. It's also in with the appendix with the tables. But you notice here we have t of sub 0.10, 0.05, 0.025. These are kind of like your z values that we had for the normal distribution when we were doing confidence intervals. We're going t sub alpha is the t value that the area to the right is going to equal alpha. So again, kind of like our z sub alpha, except this is with the t table. And we come down and we say for each, we look up for degrees of freedom. So if we look at this 1 degree of freedom, you notice if we're going to 0.005, that would be a 99% confidence interval. That t value is 63.657. Versus with the normal, you're pretty close to your 3 right there, because 3 standard deviations has pretty much everything. But, once you get down to here, we're getting down to 7 degrees of freedom, a sample size of 8, and we're down to, say, this 98% confidence interval gives us mostly between 3 standard deviations. So we're getting pretty close there. How do we use this? There we go. This is going to look pretty familiar. Again, assumptions, we need a simple random sample. And we need either a normal population or a large sample so we can say we're approximately normal with our sample. But the main difference between this and the z-interval procedure is here sigma is unknown. We don't know the standard deviation for the population, so we're working off of the standard deviation from the sample. So first, we got to figure out our confidence level to get our 1 minus alpha, so we can find alpha, and we can find t sub alpha over 2, because again, we're going to split what's left into 2 equal parts. But we also now need to consider ourselves with degrees of freedom, and that's the sample size minus 1. But once we have that, we're doing the same thing. Our confidence interval, we're taking our t-score versus our z value here, times the standard deviation over the square root of n. We're just using the sample standard deviation here. And we're using a t versus a z. And x bar minus, x bar plus. Interpret the confidence interval. How we use it, the properties of this, the guidelines, exactly the same as we did in section 2 for the z-interval procedure. It's just a way we can deal with this fact that we're working off of the sample standard deviation instead of the population standard deviation. So let's give this a try. Here we have a simple random sample of pickpocket offenses. We want a 95% confidence interval for the mean loss of all pickpocket offenses. So give this a try. Pause this. See if we've said enough that you think you can figure this out. Then come back on here and I will work through this and also show you a few things that if you haven't figured out yet might make some things handier. as we're working through this, first thing we're going to need to find is X bar and S. And here's something that will help you if you haven't figured this out yet. I haven't talked about this in class. I keep meaning to, and it's been a weird year. To use I'm going to describe how to do this with the TI-85, or sorry, not 85, with the 83, 84, because I know that's what most of my students have. But to find these values pretty easily, instead of having to add them all up and do that, use our lovely formulas for this. If you go into Stat Edit, you can type in all your numbers. I know you're good with that. But then go to Stat, and then go over to, instead of under the Edit menu, go one over to the Calculate menu. And you're going to choose your one variable statistics. And there, just make sure if you have the 83, it's going to automatically assume you want list 1, and you just hit that and enter and you're good. If you're on the 84 and you have the stat wizard, you want to just make sure that your data is looking at your list 1 and go and calculate that, and that will give you a list of things including the sum of the x's, sum of the x squareds, the mean, the standard deviation. It'll give you both S and sigma, so you have to make sure you use the right one. So it doesn't know if you have sample data or population data, so it gives you both versions. It'll also, if you keep scrolling down, it gives you your 5-number summary. So that's kind of nice easy way to get this. So we can get X, the sample mean is going to be 513.32, and the standard deviation is going to be 262.23. Now we want a 95% confidence interval. So that means alpha is going to be 0.05. So we're trying to find t of 0.025. Because again, we got to take alpha divided by 2. We have 25 values on here. So my degrees of freedom, 25 minus 1 is 24. So when I look that up on my table, so I go back to that table, I look under T sub 0.025 on the line for 24 degrees of freedom, and I will get my T value is 2.064. Now, one of the things I didn't do, that I probably should do, we still have to answer, is this normally distributed data? One thing I do want to mention, one of the sections that we skipped, but if you go farther into statistics, you will learn more about doing a normal plot, which is a way to take a set of data and see if it looks like it's normally distributed or not. That's something, depends on your software package. Some of them will generate it for you. We didn't worry about it in our class, but it's something you may see in the future. But another thing we kind of talked about were outliers. So we're going to just look and see, are there outliers with this set of data? Because again, so outliers, easiest way to do this is look at the box plot. Now again, with your graphing calculator, once you have your data in here, we can set up your stat plot, which is you're going to use second y equals, and you're going to want to look at when it goes to the plot. Normally we do a scatter plot, but if you look at one, there's going to be one with a picture like this. I think something like that. That's going to give you a box plot with outliers. And if you select that and graph that, your calculator will graph it. I'm going to do it here with decimals because I also want to show you that. Now, the command in decimals for making a box plot is pretty simple. It's Boxplot. If you bring up the keyboard here under functions and you look under distributions, here you can pick a box plot from there, and that'll put that in there. I had this set up. For the box plot, you have to type in, though, all of the data. So I have set up on here already. I typed it in ahead of time. All 25 of those numbers. Go back to the beginning. So after the box plot, you put a parentheses. Then you need square square bracket to show that's my data, and you put in all the numbers in with columns following. And you can do offsets and heights and play with this to make it look nice. But I've already reset my scale to go up a little past 1,000 because my biggest number was, I think, 1,040 something. And if we look at this, you can see my interquartile range is, well, I look at my whiskers and that's no way near, that's about the same as the interquartile range. So there's no outliers, and I don't have outliers. I'm not a large sample because I only had 25 numbers. I'm pretty close, and I can see there's no outliers. So I'm going to go ahead with my analysis, my confidence interval here. So once I have this, I'm going to take, again, x bar plus or minus. We'll just go x bar minus t of alpha over 2 times standard deviation over the square root of n. And plus. So when we got all the numbers up here, so x bar was 513.32, t is 2.064, s is 262.23, and the square root of 25. Oh, isn't that convenient and nice? That's going to give us a minimum value of 405.07. And here we do the same thing, 513.32 plus 2.064 times 262.23 square root of 25, 621.57. So your confidence interval is going to say, we're saying that the population mean is going to be, we have 405.07 to 621.57. And we are 95% confident that mu is going to be between those two values. That's the process of working with the t distribution. We don't know the population standard deviation. We're working it off of the sample standard deviation. So now let's look at another set of data. Give this one a try on your own. Then come back. How many times do I have to do that? Okay, when we look at this data here, I'm going to start off with my box plot. Let's go up to there. When we look at this one, this tail is this whisker is much, much longer than 1.5 times the IQR. This one has outliers. So this one, and we have a small data set. There is 17 numbers on there. So we're really looking at just on the very tail end of a medium size. So we're kind of iffy with this, and with an outlier, we're really not happy with it. So the outlier comes from, we look at this data, we have this 0 in here. Now, we can probably justify taking that one out because we can say, well, if we're looking at a year's chicken consumption, either someone put 0 because there's a mistake there, or you have somebody that eats no chicken whatsoever. And we can say, well, we're probably, maybe, unless we're looking at a different set of data on, do you eat chicken or not, we can say we're going to limit our population to people that eat chicken. And then we can say, hey, if you put a 0, you don't eat chicken, we don't count that. So we can justify taking this out and looking at it without that outlier. And so that's one of those things. When you're doing this analysis, if you're going to do that, you have to have a justification, and you have to make sure you spell that out when you're explaining it. So if we take here on our box plot, find the 0, say bye-bye, and we look at this box plot now we're looking much better. Again, here, this is a little bit, but it's still not close to, if we go about IQR is about that much, it's definitely within 1.5. So we're good with that. We're going to continue on. So once we're doing that, so I'm going to go back to my calculator and let it do the work for me. So now my X bar is going to be 67.13. And my S is going to be 11.11. I'm now down to 16 pieces of data, so I have a 15 degrees of freedom. I have a confidence interval of 90%. So alpha is going to equal 0.1, so I need T of 0.05 with 15 degrees of freedom is going to give me 1.753. So when I plug that into my formula, I go 67.13 minus 1.753 times S, 11.11 over the square root of 16. I will get 62.26. And if I go 67.13 plus 1.753 times 11.11 over the square root of 16, I get 72. So I am 90% confident. I just can't spell confident. That the mean chicken consumption is between 62.26 and 72.00 pounds per year. Now, if you did this on your own and you did not take out that outlier, you would have gotten, what we got here? X bar is 63.18. S is 19.51. So your T of 0.05 with 16 degrees of freedom was 1.746. And your confidence interval for that was 71.44, 54.92. So if you worked it without taking out that 0, this is the values you should have gotten. You notice taking out that one outlier pretty much cut my standard deviation in half. Made quite a bit of difference too to the mean. It went down, 4 pounds? That's because, again, mean is not resistant, so an outlier can make a huge effect on there. So I got a much wider confidence interval. I got a higher margin of error on that. So that's your t distribution. So go ahead and work on these problems, practicing using this.